Hi everyone, welcome to the fifth lesson for topic 4.4 Newton's laws of motion. So for today's lesson, we are going to continue the previous learning outcome, which is how to apply Newton's laws of motion to the linear motion of a particle of constant mass. Okay, so previously we have focusing in a part where the particle is a single particle. So we talk about the vertical motion, the horizontal motion, and the motion on a slanted plane, right? So starting from today's lesson, we'll be looking at the problems, which is the motion of connected particles. Okay, so it will be relating to the part where we discussed tension in the previous lesson, but in the previous topic, we only focusing in a part where the tension involved is for the state in equilibrium only. So which means that either is at rest or is like moving in a constant velocity. So starting from today, meaning that the smooth pulley that you will be looking at is like the particle will be moving. All right. So we'll be using Newton's second law of motion, the F equals to ma in the situation as well. All right. So for today's lesson, we'll be looking at the part the smooth pulley is over a vertical string. So there will be different kind of pulley that you will be encounter under this chapter. So it will be a vertical string one. So this is one of the very popular one in your exam. Then after that, we have the other one, which is like, for example, you have a smooth table. Then after that, maybe something like this. And the pulley is actually like this. So you have one particle here, then you have the other particle here. Okay, then the other one will be a slanted one. So maybe the pulley is here, then you have your particle here and you have your particle here. Okay, so to not make you like very confusing in our first lesson, so for today's one, we'll be looking at the first one only. So to make sure that you understand the whole idea and how do we use a combined system concept to actually solve that up. Okay, so basically that's what we want to do for today's lesson. All right, so let's start with the quick revision and also some introduction. All right, let's do a quick recap on the knowledge we learned previously about pulley system. Okay, so you know that if let's say this is the string, so when we try to put a string onto this pulley system, so what happened here is that you can see that the pulley system actually helps us to change the direction of the spring, right? Then after that, because of we are using a pulley, which is a smooth one, so which means there's no friction involved. So the tension over the string will be always the same. So let's try to look at this. So we know that if let's say this gives us the weight 1 and this is weight 2, okay? But these two particle is actually tied on the same string under a smooth pulley. So that's why it will create a tension in the string itself. So which the tension move inwards, right? So that's why this is the tension and the tension. Okay, and the tension will be just the same along the line. So a string that we normally use in a pulley is a light one. Okay, so light, which means the mass is like very small, so that we can just try to neglect it. Okay, because if not, then you can imagine that when the pulley is trying to move around, right, then after that the mass of the string is going to affect like the particle as well. So that's why it's very difficult for us to find out what's the motion over there. So that's why the string that we will be using is always a light one, and the other one is the word inextensible, if you still remember. Yeah, so which means the string cannot be stretched, so which means it's not like a springy one, which you can try to make it longer or make it shorter. Okay, so when the tension exists in the string, we say that the string is taut. Okay, it as if it's a tight lah. Then after that, if tension does not exist, so which means the string is actually in slack. Okay, so which means this is like a taut one, then a slack one maybe is like this, which means like there's no tension, there's nothing that pull the string in two side at the both end there. Okay, so now we'll be looking at this part, which previously we talked about forces in equilibrium, right? So for this lesson, we are talking about F equals to ma, which means the pulley is going to move now. Okay, so let's try to look at this pulley system. So we can try to imagine that if let's say this block is actually bigger than this block, right? So we try to assume that the weight or the mass for this particle is actually bigger than the other one. Okay, so what happened here is that by using like a general knowledge, then you will know that the pulley system is actually, I mean, the string is going to move towards the other side. Am I right? Because this is going to be heavier. So what happened here is that the pulley will become like this. Okay, so which means that what happened here is that this particle will actually move in the direction going downwards, right, with a certain acceleration. Then after that, for this particle, it's going to move upwards, okay, with a certain acceleration as well. Okay, so my question here is that, do you think that this acceleration will be the same? Yeah, so you can imagine, right, there's only these two particles at both end of the string. So that's why if let's say we say that the string is inextensible, right? So which means we cannot like stretch this string become longer than this become shorter. So what happened here is that how much the first particle is moving downwards is exactly the same with how much the second particle is moving upwards. So that's why in this case, right, then we can actually see that the acceleration for both particle here is actually the same in terms of magnitude. So although you can see that one is moving up, one is moving down, one is moving up, so which means the direction is different, but the magnitude will always be the same. So if let's say we try to denote that going down is a positive direction, then going up is a positive direction for these two different objects, then which means their A will be exactly the same. Okay, so the same thing now, if let's say the acceleration is the same, right? So which means when the particle reach this stage, so which means that for how much this particle moving up is exactly going to be the same thing like how much this particle moving down. So by using the idea of, the Suvat formula, and you can actually imagine that if both of these particles is at rest, so which means they have the same U, they have the same S, then they have the same A. So what does that mean? Which means that at the part here, the velocity here and the velocity here will be exactly the same as well. If let's say we try to denote like going down as positive and going up as positive for these two different objects, so which means the magnitude will be always the same without looking at the direction. Okay, so you can see by writing down this alphabet, I actually meant that for example, the weight 1, weight 2, I am trying to denote that it's a different value. So you have W1, W2. So the other one, the tension is the same. So that's why TT, I did not put like T1, T2. So same thing, A and A, S and S, and V and V. Okay, so remember this idea, and now we'll be looking at the first example before we come back for this part. Okay, so we'll be looking at 3 past year questions for this lesson. So which means for the first one is like a very simple one for you to understand how do we solve it by using Newton's second law of motion. So no matter we are trying to treat the connected particle in a form of individual particles, so which means that we try to look at it separately. After that, we also try to look at how do we solve it by using an idea of combined system. Then the second example will be looking at the greatest height, like basically how the two particles move in details. Then after that, the last one will be looking at what is the circumstances if let's say the string breaks after that. Okay, so now let's try to look at example 1 so that you can understand the whole idea first. All right, let's try to look at example 1. So this is question 1 from paper 4 to March 2018. So there are these two particles A and B of masses 0.8 kg and also 0.2 kg. So they are connected by a light inextensible string. So you can see the keywords here, right? So they are passing over a fixed smooth pulley. So which means there's no friction involved and the tension over the string is actually the same. So the particles hang vertically, all right? So let's try to draw the pulley system maybe. So this is like the smooth pulley. So we have the particle A here. All right, so maybe this is the 0.81. So the weight here is actually 8 Newton. So we have this particle A. Then after that, same thing, we have the other part which is here. Okay, so this weight is actually 2 Newton. Sorry, it's a bit ugly, but yeah, as long as you can see that. Okay, so this is the particle B. All right, so the system is released from rest. All right, so the question tells us that, which means for particle A and B, both of them is having a initial velocity of 0 lah. So show that the acceleration of A has magnitude of 6 meter per second square and find the tension in a string. So you realize that in this kind of questions, right, normally the two things that is like they normally ask is the acceleration and also the tension. Okay, so you'll see over like the other question as well, so like the same element that they try to ask. All right, so now let's try to look at this picture. Okay, so we know that this is the weight, so the two particle is connected by this string, right? So that's why there's a tension here going up. Okay, and because of this is a same string and the pulley is a smooth one, so that's why the tension over the line is actually the same. So now let's try to imagine how's the motion of the particle. So we see that the particle A is having a higher mass, am I right? So even the weight also is at 8 versus 2. So that's why we can imagine that how the pulley is going to move is going to move over this. Am I right? So that's why there will be an acceleration that's going down. Then after that, for this particle, then it will be an acceleration that's going up. Okay, so which means the motion of the particle is like one moving downwards, one moving upwards. All right, so we'll try to attempt this question by using two different approach. So the first one is by using a separate particle. Okay, so this is the idea that we have learned previously. So yeah, let's try to look at them like individually. So this is the first approach, which we try to look at it separately. Okay, so let's try to look at particle A. So for particle A, so we'll try to, so-called like resolve it, but yeah, actually we don't do any resolving, that is just by equating the force. So you know that the net force is equal to ma, right? So that's why this particle is moving downwards. So moving downwards is our positive direction. So the mass that is in the positive direction is the weight here. So that's why weight minus of the tension will be equal to ma. So the mass involved here is 0.8. Then after that, acceleration is 8. Okay, so that settle our first equation. All right, so by using net force equals to ma. So similarly, now we try to look at the particle B. So for particle B, we try to denote that moving upwards is positive, right? So that's why we have our tension in a positive direction, that minus of the weight, and it will be equal to the mass here is 0.2, and the acceleration will be a as well. Okay, so you see, right? Let me try to explain it a bit. Why do we want to denote different direction for different object? Is that if let's say you try to, for example, for this part, if you try to note that going down is your positive direction, right? Then what happened here is that your acceleration here will be changed to negative a instead, because you can see that for the velocity for this one, right, it's moving down, this one is moving up. So that's why they are actually in a different direction. But now we are trying to make them into the same phase, which that I can try to solve it by using like they are having the same magnitude of A. So that's why we want to make sure that both our A is positive. So I do not need to deal with like so many confusing the negative or the positive sign. You get what I mean, right? So that's why it will be easier for us to actually denote two different direction as the positive direction based on the motion of the respective particle here. Okay, so by doing this, then both of these will be having the same A, because for this part the positive is going down, for this part the positive is going up. Okay, so that's the idea. So that's why we don't need to do like negative A. Okay, so by having equation 1 and 2, so now we can solve it. I think we can just plus them together, right? I think this is good for me to, yeah, this is part 1, so not to confuse with this. Okay, so the first equation plus the second equation, then I have negative t plus t, right? Then after that t plus, so which means 8 plus negative 2, and it will be equal to 0.8a plus 0.2a. So from here I can get A. So A will be equal to 6 meter per second square. So you see I prove it. Okay. So after we got this, then we need to find the tension in the string. So you can use either equation. So I'm using the second one. So T minus 2 equal to 0.2 multiply 6. So 1.2 plus 2, and I'll be able to get 3.2 Newton. Okay, so that's it for the first approach. So now we'll be looking at the second approach, which is how do we solve it as if treating them in a combined system. Okay, so yeah, this is very interesting. I think this is very helpful as well when we try to move on to other question. So you can try to imagine what happened here is that this is our system, right? When we try to look at it in a complete system, so which means this is actually the thing. Okay, so when we try to look at it as if a combined system, right, which means that we want to solve them in one. Okay, so what you can imagine is that, can you see that actually this is the tension going up and this is a tension going up as well, right? Then we have the weight here, then we have the weight here. If I were to redraw this, right, how can I actually do it is that because this one has no friction, what? So if I try to rearrange, I mean, I try to redraw this whole thing in a horizontal plane, then how is that going to look like? So I will be having a particle over here and I have a particle over here. So this is like the string. So this is a pulley, right? So I mean the pulley doesn't create any forces. So which means there's no friction over there. So yeah, I mean that's the part where we have the tension and we have the tension as well. So you can see that the two tension, right, actually eliminating each other. So we have this one, which is the weight over the other side. Then we have the weight over the opposite side as well, right? So this is the part where I have my W here is like 8 Newton and then the 2 Newton. So which means when we try to treat it as a combined system, what we have is that you can see that it's the same thing that we try to use. The net force will be equal to MA. So what is the net force in this? So we know that this is 8 Newton. So for sure that this system will actually move to this side. Am I right? The acceleration going down is positive. It's the same thing like when we try to look at this, then going down is positive. But we are just going to look at in a horizontal element. So that's why now the net force will be equal to, so T and T, they eliminate each other already. So that's why the net force in a positive direction, we have the 8 Newton here, and then minus off the 2 Newton that going to the opposite direction. Then equal to what's the mass here? So the mass will be the total mass, right? So the total mass that we have is actually 0.8 plus 0.2, and then the acceleration. So you'll realize that what we have over here, right, is basically exactly the same like what we have over here when we try to plus them together. So this is like a combined system. So 6 will be equal to A. So by having this, then you actually solve your first variable already. So normally this is very helpful if let's say you don't want to do simultaneous equation. So because of you are solving it as a combined system, so the tension will normally just cancel out each other, so you can find your acceleration first. Okay, so after you get your acceleration, then you need to use the same part to actually solve the tension lah. You don't have a choice over here because you cannot treat it as a combined system, then you do not have the T, then you cannot solve it. So you can use either one that you like. Okay, so for example, for this, if let's say we try to denote going left is the positive direction, then we just try to do the same thing lah. So this is for particle A. So we have 8 minus of the tension will be equal to the mass, then multiply with 8. So 8 minus T will be equal to 0.8, and 6 is the acceleration. So we get T equals to 8 minus 4.8, and that gives you the exact same answer, which is 3.2 Newton as well. Okay, so there are two different approaches that you can try to choose yourself. So it's either that you have simultaneous equation, then you solve them. I mean, when you try to solve the simultaneous, you actually get the exact same equation as your combined system as well. Okay, so you can solve your acceleration first, then after that move on to your tension. Alright, so I hope that by using this question, you can actually have a better idea on how everything is going to work out in the Pulley system. So we'll be looking at the harder question now. So just some further knowledge is that you can see that both of them having the same acceleration. So that's why like what I mentioned previously. So which means if let's say the pulley reach a certain stage like this and then this moving up, right? So remember that the velocity here and the velocity here will be actually the same lah. So when we try to denote that going down and going up is a different positive direction. So the two, the WA and WB, sorry, VA and VB is actually going to be the same as well. Alright, so now let's try to look at number two, and we will try to look at the motion on a pulley in a much detailed way before we attempt the question, so you have a better idea how are we going to solve that. Alright, so this one will be looking at what happened for each particle to be exact when we try to especially Alright, so for this one, we'll be looking at what's the motion of these two particles respectively when there's a motion on the pulley. Alright, so this is very helpful if let's say the question want you to find the greatest height, and this is one of the very popular question in your past year paper as well. Okay, so let's try to look at this. Yeah, the thing that I just want to put in place first is that please remember that the line that I try to draw here is like for an illustration. So when you try to look at this particle, right, so do not have the doubt where, I mean, for the distance, is it from the top of the object, from the middle of the object, or from the bottom of the object? Okay, because in the real situation, we are just looking at the motion of a particle. So you know, a particle is like a very small one, so it actually doesn't matter much, no matter the distance that you are calculating is actually from the middle, from the top, or from the bottom. You get what I mean? So that's why this is like for an illustration for you to see like the difference of, I mean, the distance that I have later only. Okay, so please do not get yourself confused with whether I want to draw the line in the middle or what. Yeah, so that's the idea. Okay, so similarly, let's try to assume that by having a bigger block, so the mass here is actually higher. So which means I have this weight 1, then weight 2. Okay, then these two particle is connected by this pulley system, so that's why we also assume that this is a smooth pulley, so the tension over the string will be the same as well. Okay, so because this particle is having a larger mass, right, so that's why we know that the pulley or the string will actually move in this direction later. Okay, so this particle will be moving downwards, so we'll try to denote it as positive going down. So this particle is going to move upwards, so we try to denote that going up is positive. Okay, so if let's say this particle is at rest, okay, at the initial stage. So what happened here is that we know that the final velocity for these two is going to be the same as well, right? Okay, so now let's try to draw what happened for the second stage. So this is a taut one, so which means the string is taut. Okay, so there's tension involved. So for the second stage, right, we can imagine that after we try to release them, then what happened here is that the pulley will move in this direction. So that's why now the pulley will actually look like this. Oops, I'm sorry. It should be a straight one. You can try to use your ruler to draw it. So a straight one. So now the object is happen to be here. Okay, this is my particle A. So maybe this is A, this is B. So this is my particle A here. Then my particle B here will actually move up and right. So this is my B. Okay, so from the picture and from what we discussed previously, we also know that if let's say how much because the string here is actually still taut, so how much the particle A move is basically the same thing with how much particle B move. So that's why if let's say this is SA and this is SB, so the SA and SB is actually the same, right? Okay, then after that, let's continue to look at this diagram. So if let's say, I mean at the initial stage, both of this particle is at rest. So that's why we just now we know that the magnitude of the acceleration is the same, right? So that's why having the same u, same s, and then the same acceleration you will have the same final velocity as well. So which means if let's say after the particle reach this stage, so it will reach a certain final velocity, right? So this is like VA, then this is like my VB. Okay, and I also know that my velocity for A and my velocity B will be the same as well. If you try to denote going down as positive, then going up as positive for these two different particles. Okay, so now you see, right? I want you to try to think about this. This is my first stage. That after I release, this is what happened. Okay, so my question is that do you think that the pulley will actually stop here? So how logical do you think that this thing will actually move down, then this thing will move up, then after that it's like a very perfect motion, then after that it stops like that? Okay, so you see, right? Then if let's say I want you to try to find what is the greatest height that can be achieved by the particle B, then what's your answer? Is it going to be here? Okay, then here comes the other question. So if let's say this two particle is at rest at the initial stage, right? What do you think is the velocity here? So I do not know what's the velocity, but one thing that I can confirm is that this final velocity wouldn't be zero. Am I right? Because it has a certain acceleration that causing it to move up. So that's why if let's say this two particle is at rest, then obviously you have the final velocity as if it's not going to be zero. If let's say this is not going to be zero, right, we also can assume that this particle wouldn't actually stop there. It's just that there's no tension anymore. There's no continuous tension anymore. But there's still velocity over there, right? And what is the thing that actually affect the motion now? It's actually the gravitational acceleration. So which means what happened here is that you can imagine that when we try to release it, right, this thing is going to touch at the bottom here, but then this thing is going to fly a bit up. So which means that the string now is going to be like a bit slack. Then after that, it's move up a bit until it reach a certain part where your final velocity becomes zero. I hope that you get what I mean. So which means this is like the pulley. So this is what happened. So when you first release, right, then it will go down. Then after that, this thing will eventually not stop here, but it's go like this. Then after that, the thing will actually flies up a bit. Then after that, until the velocity is reaching zero, then after that, it drops back again. So that's why we have this stage which the particle will actually looks like this. So this is when the string is actually in circumstances of slack one. Okay, then after that, after it becomes slack, right, then your final velocity is zero. Then after that, because of the gravitational acceleration, then this thing will actually drops down, right? Then it becomes taut again. So this is the final situation that we see. Okay, so yeah, we are not looking at part of this, but we want to understand this part. So you can see, right, when this string becomes slack, so what happened here is that it's not because of the A causing by the tension anymore. Is because of, after the, okay, you see, what is that meant by taut? What is that meant by slack? Is that taut is with tension, then this one without tension. So if let's say there's no tension anymore, which means you do not have any net force and you do not have the A already, right? So that's why what is causing by this is actually caused by the gravitational acceleration. It's same thing like whether it flies up or after it flies up, then it reach a certain maximum height, then after that it drops down again. So it's both caused by the gravitational force. So the A here is actually the negative G that we have because G is like going down, so negative G going up. Am I right? Okay, so at this point, right, then what you can see here is I will have my velocity for, how should I write this? So my initial velocity is actually equal to my VB here. So I'm going to put a star here. So this is like for second stage. Okay, Then after that, because of this A, then it's going to decelerate the motion, right? Then after that, it's going to give you a final velocity of 0. Okay, so I want you to remember this idea. Then now we'll be looking at an example. Then you will see how is this going to make you going to make the answer to be different when we try to talk about the greatest height. Because the greatest height then can be achieved by this particle is not this height only, is the height after it is affected by the gravitational acceleration as well, so that the final velocity becomes 0, then that's the greatest height. Okay, so that's the idea. So now let's try to look at example 2. I hope that you can roughly understand this idea here. Alright, so this is a past year question from paper 4 May June 2016. Okay, so there are two particles of masses 1.3 kg and 0.7 kg are connected by a light inextensible string, again passes over a fixed smooth pulley. Okay, so the particles are held at the same vertical height with the string taut. So okay, maybe let's try to draw it out. So we have this smooth pulley. Then after that, this is our first particle, which is 1.3. So which is 13 weight. Then after that, the second particle over here, okay, which this is 7 Newton. Okay, so the particle is held in the same vertical height, so which means, yeah, they are in the same vertical height lah. Then the distance of each particle above a horizontal plane is 2 meters, so which means this is the horizontal plane maybe. So we know that from here to here is 2 meters. Then the distance of each particle below the pulley is 4 meters, so which means here is 4 meters. Okay, sorry, it's not obvious in the picture, but yeah, that's the idea. So the particles are released at rest, so which means both of them, the initial velocity is actually equals to 0. All right, so yeah, you can see the question. The question again asks for the tension. Okay, so normally when you need to find the tension, then which mean you need to use net force equals to ma. So I mean indirectly you'll be finding your acceleration as well. Then after that, the question want to find what's the time taken for the particle of the mass 1.3 kg to reach the plane. So you can imagine that you will need to use Suvat formula. Then after that, we need to find the greatest height. Okay, so now let's try to solve one by one. Let's try to look at 1a first. Alright, so the tension in the string before the particle of mass 1.3 kg reaches the plane. Okay, so which means before you try to so-called like release it. So we have the tension, then we have the tension. Okay, so yeah, this particle is heavier, right? So that's why going down as positive for this side. Then this part will be going up. So we try to denote going up as positive. So this pulley will move in this direction actually. Okay, so now let's try to solve it. So yeah, I think we can try to do a combined system so to actually make yourself like get used with it. So that's why we know that the whole system will actually move to this side. So that's why the net force, it will be equal to 13 minus of 7. So remember, combined system, no more tension because they balance off with each other. Then equal to the total mass 1.3 kg and then plus 0.7 kg and multiply by 8. Okay, so from here that I can get 6 equal to 2a. So I will have a equal to 3 meter per second square. So after I got this, then yeah, depends on you. You can choose either one that you like. So if let's say you try to use 13, so for easier cost, so 13 minus of the tension will be equals to the mass 0.18. I'm sorry, it's 1.3, not 0.13. So 1.3 multiply the mass, sorry, the acceleration 3. So from here, then I can get 13 minus of 3.9, and that will give me 9.1 Newton. Alright, so by using it, then I solve for number 1, which this is the tension that I have. Okay, so normally, no matter you are treating them in a separate particle or in a combined system, you will actually find the acceleration first in most of the case. Okay, so time taken for the particle mass 1.3 to reach the plane. So this is for part B. Alright, so what we have here is we know that the initial velocity is 0, then the acceleration is 3. Okay, so please do not assume that the final velocity is 0 lah, is 0 yeah, because we cannot actually confirm that. Yeah, Okay. I mean, this is acceleration. So by using a common sense, you should know that the final velocity wouldn't be zero. Okay, because yeah, you're actually the velocity is actually changing, right, with this acceleration. So it's like getting bigger and bigger. So from rest, then after that to a certain number of final velocity that only this thing can move. Then after that, what else do we have? Yeah, the question tells us that this is 2 meter, right? So that's why for this particle to actually reach the plane here is going to be the displacement of 2 meters. So that's why S is 2. Okay, and the question one is to find T. So subvert here UAST, then we can try to use S equal to UT plus half AT square. So let's substitute 2 equal to 0 plus 1 over 2a t square. Okay, so from here then you will be able to get your, yeah, I'm not going to solve the max thing. So it's basically you will get 1.5. So 2 divide 1.5, we can get 3. So from that then we can have t will be equal to 1.15 second. Okay, so this is to 3 significant figure. If you were to write it in exact value, then it's 2 square root 3 over 3. Okay, so you can write both. I mean, you can just put your answer like this. So yeah, always write in 3 significant figure. I think that's good. But if let's say you want to write your exact value, then you can always do it like this. Okay, so 3SF. Alright, so remember after you solve this, then your answer should be square root, and this is how you get to this. Okay, so now we solve for part B. So now we try to look at part 2. So this is the one that I tried to explain just now. So yeah, I mean, if you try to use the idea of, you see, right, if let's say we do not have the third stage, which is the string is taut, the string becomes slack. So what happened here is for number 2, you actually don't need to do anything, because how much the particle A move will be exactly with the same thing with how much the particle B move up. So that's why your answer can be 2 meter. Then the question do not need to ask for the greatest height. You get what I mean, right? So let me try to draw it up. So which means this is your first stage, right? So after that, just now from what we did here, the first particle, is it A, B? No, yeah, the first particle here is actually reaching the plane already. So that's why what happened here is that you have the plane. So this is already here, then this one is going up here. Okay, so which means that now this become like the 2 meter. Am I right? Because 2 meter going down already. So that's why this particle is going 2 meter up. So that's why this is like the 4 meter here. So if let's say you don't understand the idea of the third stage, then what you will tend to do is your answer will be just 2 meter lah, because this is like how much it move up. So the greatest height that for the particle of mass 0.7 kg is basically 4 meter. But that's not correct, because of we know that the final velocity for this particle is not equals to 0 yet. So that's not the maximum height. So what happened here is that from what we discussed just now, so this thing will eventually like fly a bit. Okay, so either you want to draw it slack or you draw it just like flying up high a bit lah. Then after that you have this thing. Okay, so now any information that actually can help us to find, because you can imagine that what you need is to find the distance. Am I right? So something that you have here is, maybe we know that the acceleration here is caused by the gravitational, right? So that's why moving up as positive, then this is negative 10. Okay, then we know that at the maximum height, the v is equal to 0. So we need one more information. Either we need what is the time, or either we need the velocity, the initial velocity. But in this case, we know that we wouldn't able to actually find, I mean, the time for this one is not the time that for this, okay, the time for this particle to reach this place is 1.15 seconds. So it's the same time for this particle to actually move up when the string is still taut. But when this particle reach the ground and this particle fly up, right, it doesn't mean that this particle will will use 1.15 second to move up as well. So that's why we cannot get this piece of information from our first particle. So what do we have is, you remember, we said that for this thing, right, this two is having the same acceleration. So that's why the final velocity for this particle is actually the final velocity for this particle as well. So this final velocity is the initial velocity for this one, right? So that's why we'll need to find what is this. So let's try to denote, maybe this is the first particle and this is the second particle. Okay, so C. Oh, is it C? Sorry, this is part 2. Alright, so which means what happened now is we want to find the initial velocity for the second particle for the third stage here. It will be equal to the final velocity of the second stage here for the first particle. So now we have U is at rest, right? So let's try to use back the exact same information here. U is 0, A is 3, and S is 2. I will always try to avoid to use the thing that I find in previous question, because if let's say my T is wrong, then that will cause my part 2 to be wrong as well. So that's why I try to use the information that given in a question, or the information that you are much more confident, I will say. Okay, then we can get what's the final velocity. So v square will be equal to u square plus 2as. So that will give us 0 plus 2a then s. Okay, so from here I can solve that v will be equal to 2 square root 3 meter per second. So for this one, it's okay because this is not what you want to find at the end, right? So do not need to round it off because you need the exact value later. Okay, so that's why we know that the u2 here is basically equal to 2 square root 3. Okay, let me try to explain it again. I hope that you can understand. So when this thing reach here, is actually equal to 2 square root 3 meter per second. Okay, so because these two particles share the same acceleration, so that's why, I mean, this going out as positive, then this one going up as positive. So that's why they have the same velocity here, which here will be 2 square root 3 as well. So this thing start to fly up. So now we need to look at it with a different stage, because you are having a different acceleration now. The tension is no more in this stage. Okay, the tension of the line is no longer exists here because the string here is flat already. There's no tension. So that's why in this case your A is actually affected by the gravitational force, which is -10. So the here you are having the u as 2 square root 3, which is the end of the second stage here. Then v is equal to 0, a is -10, and we want to find what is the s. Okay, so with this variable, then we can use v square as well. So 0 equal to u square plus 2as. Okay, so from here we can get our s is 20s equal to 12. So s will give us 0.6 meter. Okay, and don't forget this is not your last answer out, which means previously the line is here. Okay, so that's why from here to here is 0.6. And we want to find the maximum height, the greatest height of the particle above the plane. So which means the plane is here now. Okay, so just now we know that when the particle is here, this is 4 meter, right? Then you're moving up for a further 0.6 meter. So that's why the greatest height from the plane okay, will be equal to, either you want to do 2 plus 2 again, or if not, then you just 4 plus 0.6. So that will give us 4.6. 4.6 meter. Alright, so yeah, that's the idea. You will actually encounter a lot of this question in your past year paper. So try to understand. So yeah, basically in all the cases, they will be the same lah. So you need to understand that how this thing move. So when the string is still taut, then you reach the second stage. Then after that, what happened here is that because the final velocity here is not 0 yet, so we can assume that this thing will actually fly a bit up. So that's why the string now is taut, the string now is slack. So that's why if the string is slack, there's no tension, and your A will be the gravitational force. So that force you to actually create another Suvat formula because you are having a different A now. Okay, so that's the idea. Okay, so how do you get the initial velocity of this one is to find the initial velocity of your first particle reaching the ground and so on. Alright, so now we'll be looking at the last example here, which we'll be looking at how if the string breaks after that. Alright, the last question. So, two particles A and B have masses m kg and km kg respectively, and given that k is greater than 1. Okay, so yeah, you might wondering why do they give this is that you can imagine this is m and this is km. So if let's say k is greater than 1, so which means you can imagine this might be 1.1 m or like 1.2 m or like 2 m and so on. So that's why it actually indicates that for particle B, it actually has a higher mass. Okay, so which means later when we try to look at this, then the pulley will move in this direction. So which means this will be moving down. Okay, so this will be actually moving up. Alright, so the particles are attached to the ends of a light inextensible string. The string passes over this fixed smooth pulley. So the particle hang vertically below it, and the particle are at a height of 0.81 above this horizontal plane. So the system is released at rest. Then the particle B reaches the ground 0.9 seconds later. So the particle A does not reach the pulley in its subsequent motion. So which means that the particle A is somewhere still here. So which means it didn't like pass over the pulley lah. That's the idea. So find the value of K and show that the tension in the string before B reaches the ground is equal to 12 m Newton. So you'll realize that in this question, there are actually much more variable that we need to get. So for example, in your mass, you also have one variable, which is the K that we want to find. Then after that, we want to find the tension. So which means in other words, we also need to get the acceleration as well. Okay, so yeah, which means there are three variables that involve here. Then which means by just using net force equals to ma, it will be not enough for us, because what happened here is that if let's say you are trying to put it in a combined system as well, right? So what you can eliminate is that your A will still left with your K. So by you might need to read the question again and see is there any extra information that you are given except the normal one that you will be given in like question 1 or 2. Okay, so in this thing you realize that actually you are given the distance. You are also given that the system is released from rest. So which means in other words, we know that for A and B, right, their initial velocity is actually 0. Let me try to write here. So which means that what happened here is we try to focus in particle B lah. So for particle B, the initial velocity is actually equals to U. So it spends 0.9 seconds to reach the ground, right? So which means the displacement is 0.81. Then after that, 0.9 second is our time. So by having these three elements, actually we can use our Suvat and we can get our acceleration here. So after we get our acceleration right, then we can use F equals to ma to help us to solve our K and T. Okay, so that's the idea. So what is important is you need to understand the question and extract the information that you need. Okay, so U, S, T, and A, so we can use the formula of S equal to UT, yeah. S equal to UT plus half AT square. So from here, I can get 0.810 plus 1 over 2A is what we want to find, 0.9 square. So from here, then I'll be able to solve it. So 0.81, so I will be able to get 2. So A equal to 2 meter per second square. Okay, so after I got this, then now we can continue. So either I think we can use combined system as well. So we know that as a combined system, this pulley will move to this side. So that's why what we have here is the net force will be equal to the km times g. So which means it's 10 km. Okay, remember this is your mass here, so we need to change it to weight. So that's why multiply 10. So 10 km minus of the force for the other side, which is 10 m. and that will be equal to MA. Okay, so yeah, let me try to write the complete one in case you are confused. So the net force will be equal to, so we try to look at the combined system, so that's why it's the total mass, then multiply total M, then multiply with the acceleration. Okay, so the net force here, so which means we try to look at it as like a vertical, so this is like our pulley, then after that this the weight here, then we have the weight the other side. Okay, so the net force here will be 10 km minus of 10 m. So the total mass that we have is km and then plus m. The acceleration, we got it from the equation just now already, which is 2. Okay, so by substitute it, then now let's see how can we solve it. So I think we have all m, right? Then we can try to eliminate that. So 10k minus 10 equal to k my please make sure because I already know that this one I after I expand then I'll have all term of m, so that's why I can eliminate it. If let's say this is plus and this is 2, then I cannot, I mean you can, then after that you will have 2 divided by m log, then that's like meaningless for you to do so. Yeah, so then what I left here is k plus 1, okay, and then 2. So let's try to solve it. Then I have 10k minus 2k equal to 2 plus 10. So 8k will be equal to 12. So this question is quite long because you see from the question you have 7 marks. Okay, so normally if let's say you try to look at the previous question which you have tangent and acceleration, it's normally 4 marks. So which means it's like equation, then answer. So like 4 marks. So that's why by looking at the mark here, then you have 7, then which means basically you will need to have, I mean the equation that involved here is highly more than 2 lah basically. So k will be equal to 1.5. Okay, so k is basically just a ratio here, so that's why there's no unit here. So you after you get the k, then now we can get the tension already. So use either one. So since we try to move in the go to the right hand side, so we use the same direction lah. So the weight and then the tension. Okay, so weight here is 10 km minus of the tension. Okay, then equal to the MA, the mass here is km, then the A here is 2. So let's try to substitute all the variable that we have already. So 10, then after that the K is 10, 1.5 m minus T equal to K 1.5 m, then 2. Okay, so what do we have? 15 m minus T equal to 3m. So I can get my T will be equal to 12 m Newton. Okay, that's correct because the question wants us to, prove that is 12 m Newton. So you know that for this answer, you will still have the m in your equation lah, basically. Then this is how we get to this answer. Okay, so now we try to look at the second part. At the instant when B reaches the ground, the string breaks. Okay, so what happened here is this thing is moving, right? So yeah, okay, then I think we can try to draw it. So what happened here is you have this horizontal ground just now. So this is a pulley. So what happened here is for this part, the B is actually reaching the ground already. Okay, but what happened here is that when B reaching the ground, right, then the string actually break. So I'll just draw this. Yeah, it breaks already. So, okay, maybe I draw before break first. Okay, so what happened here is this is B, then this is A. Okay, and then what happened here is that after B actually reached the ground, right, at the instant where B reaches the ground, so what happened here is that this is the ground. So B reached the ground, then A is like breaks. Okay, so you can see that by looking at the question where they use the word at the instant when B reaches the ground, because you will actually think that is it because from the question 2 just now we know that there's a stage that this string will actually fly up, am I right? But when they try to emphasize here is that at the instant B reach the ground, then A breaks. So what happened here is that you do not really have the time for the particle A to fly up. Then after that, the string is break already. So that's why this is like our second stage. B reach the ground, and then after that, the string breaks. So that's the idea. So which means the question one is to show that the speed of A when it reaches the ground is 5.97. Then find the time taken after the string breaks for A to reach the ground. Okay, so which means that when we try to go back to this picture, right? So what do they want is, after the string break, then the A will certainly fall to the ground, right? So what is the final velocity here? And what is the time for A to actually reach the ground? So this is the idea. Okay, so some of the thing that we already know is that at this place, right, this falling down, I mean this motion is no longer affected by the tension because obviously the string is already break. So that's why the particle A is under a free fall, is affected by the gravitational force, which is the A equals to 10. Alright, so now we'll need two more information so that we can use Suvat to actually help us to find our V and T. Okay, so which means the other two information that we'll need to find out is what is the initial velocity for the A here. Then the other thing is what is the total displacement for the A here so that we can try to solve our V and T. Okay, so let's start with the displacement. I guess that's easier. So by looking at this diagram, right, so what happened here is that B is actually moving down and it reached the floor. Then after that, B is actually moving up, so it reached here, right? So if let's say in this diagram, I try to note that this is basically my initial stage, right? So what happened here is B is falling down, so that's why the displacement here is 0.81. And the string remains taut here, right? So that's why this will be 0.81 as well. So that's why I know that the total displacement from the part where A breaks and it reached the ground is actually will be equal to double of 0.81, okay, which is 1.62. So now we need to find 1.62 here. So now what do we need is to find the to find the U here. Okay, so by using the same idea that we learned previously, so the initial velocity of the A at this place is actually the final velocity for the A for the previous stage, which is the final velocity when A reached the ground as well. So that's why we try to look at the particle B. Okay, so oops, I'm sorry, for particle B to hit the ground, yeah. So we have U equals to 0 because they are previously both at rest, right? So S is 0.81, T is 0.9. So similarly, I didn't use the A that I find previously. So I'll try to use the information that I get from the question. So from here, then I can use S equal to half U plus V then T. Okay, so 0.81 equal to half, then 0 plus V, T is 0.9. So from here, then I can get V is equal to 1.8 meter per second. Okay, so we know that the final velocity for B at this stage is 1.8, so it will be similarly for A as well. Okay, because how much B move is going to be exact the same with how much A move, right? So their speed is actually the same. And we try to denote that this one going up is positive in this case, then this one going down. Okay, so now we need to find out what is our time then. Okay, so this comes a problem. So you see, when we try to do this, right, we try to denote that going up is positive. So that's why the velocity here and here is the same. But when we try to solve for this motion, right, this A is actually moving down now. So that's why it's good that we try to denote that moving down is positive. So your velocity, your initial velocity for your A should be negative because this one is eventually previously is moving up one. So your initial velocity is going up, the motion now is going down, and our positive direction is here. So that's why your S is positive, right? Then the acceleration due to the gravitational force is actually positive also. Okay, so now let's continue. So how do we get to that is we already got three information, so we can try to find out our V first. So question one is to find out the speed. So we can show the speed first. So I think it's helpful for us to actually check whether the three element is correct or not. Because if let's say you can get that one, then you can roughly know that your other three element is correct. Then after that you only move on to time, right? If let's say you try to find the time, then later you realize that the speed is wrong, then the whole thing is going to be wrong as well. So that's why let's solve for the V first. So now for A, okay, so what we have here is the initial velocity is going to be 1.8. Then after that, the A is 10. Okay, I'm sorry, negative 1.8 because we want to denote that going down as positive now. Then after that, we want to find our V. Then we have our S is 1.62. So we want to find the speed, the final velocity lah. Okay, so we can use V square equal to U square plus 2AS. So negative 1.8 square plus 2, 10, 1.62. Okay, so by solving the formula, then from here, then we can get 35.64. So our V is 5.97, so which is correct. Okay, so by looking at what do we need to show in this question, so we know that the three element is correct. Okay, so you see, right, in this you realize that u square so as y, whether you negative it doesn't matter much, but it matters when later you want to solve your t. If let's say your u is wrong, then later your t will be wrong as well. So by using the exactly same element here, then we try to find t now. So U, A, S, and T. So we can try to use S equal to UT plus U, A, S 1 over 2, yeah, AT square. Okay, so we don't use you want to use the V also okay lah, because but make sure that you use the exact value, okay? So 1.62 equal to our U is negative 1.8. T is what we want to find. Half acceleration is 10. Then T is what we want to find. Okay, so this is a quadratic equation. So you can get 5t squared minus 1.8t minus 1.62 equals to 0. Okay, so yeah, in this case, we are now in mechanics. So normally the working is not very important because you'll realize that you will need to use the formula, the quadratic formula, the b square minus 4ac that want to solve this. Okay, so yeah, you can straight away just write down your answer. So negative 0.417 and the other one is 0.777. Okay, so since the time should be a positive value, so that's why t is equal to 0.777 second. All right, so this is the time that the particle spent to actually hit the ground. All right, so the last part, could sketch a velocity time graph for the motion of particle A from the instant where the system is released until A reaches the ground. Okay, the system is released, which means that you might want to, the questions one, what is the velocity time graph when A is here? Then when A reach here, then when the string breaks and it hits the ground, so which means they need the whole thing here. Okay, so I try to use a different color here maybe. So yeah. Okay, so which means we want to find what's the velocity time graph when this thing is moving up until it reach here. Then after that, the string breaks. So it falling down until this part. Okay, so yeah, you need to assume that going up as positive now lah. So everything that we've tried to find just now will be, the velocity over here will be in a negative direction instead, because you are drawing a one velocity time graph. So that's why you cannot suddenly do like A going up as positive, then after that A going down as positive. So our VT graph, so it's actually just 2 marks, so I don't think the question need like a very detailed one, but for you to understand that it's moving in as a constant acceleration, so that's why your line should be a straight line. So we try to write down some of the important point maybe. So when t equals to 0, we know that the system is at rest, right? Then after that, when t equals to the first stage, which means from here to here, is when what's the time just now? Is it zero? Yeah, it's 0.9, then it's 1.8. Okay, and then what else do we have is the last stage here. So we have t is equal to 1.677. Okay, then after that the velocity here is equal to what we have here is 5.97. Okay, but because of we are treating this part moving up as positive, so that's why this should be a negative value lah. Okay, because you see what happened is that previously the particle is actually moving up, so that's why it's in a positive direction. Then after that it falls down, right? So that's why it's the velocity is in a negative direction now, so that's why it's negative. But when you try to solve the number two here, because we are finding the speed, so that's why we just only care about the magnitude. So we just like change the sign, then that will be easier for us. Okay, so yeah, let's continue. So after you get this, yeah, then you can draw your graph already. So basically you just need a straight line. Then here is 0.9. Then here we have 1.677. This is our time velocity. So 1.8. Okay, so this is supposed to be a little bit lower. So negative 5.97. Okay, so from here to here is under the acceleration of the tension, right? So it's moving up. Then after that, this thing from here to here. Okay, so it's going down. So the question doesn't really need us to find out what's the intersection here, but basically it's for you to understand that you are using two different acceleration. So that's why you have two different straight line of having different gradient here. Okay, which one is positive and one is negative, which is correct in the terms of the direction of particle. One is moving up, one is dropping down. All right, then your velocity should be one positive because it's moving up, one negative because it's falling down. All right, so that's the idea. So I hope that you can actually understand it. So yeah, spend some time to look at the questions, then try to understand it. If you have any question, then feel free to just ask me personally. Okay, so that's the idea. So thanks for watching. Yeah, see you in the next lesson.